Test, test. All right, guys. I know this is a little bit different. I don't know if you can hear me. If one of the interns can just text me to make sure. We're gonna try to do this today remotely. Unfortunately, my daughter is sick, so I'm home today. Um, all right, I got the so what I need you to do, I know the interns probably told you, but what you need to do is if you have the worksheet with the different waves and also the packet with this first page, what I need you to do is match my colors just for this. That's all you need to do. And for the do now, you're taking a picture of both of these side by side and then turning it in and then just waiting. All right, we'll probably start about 9:15. That should give you all enough time to do the coloring. If you have any questions, please send me a chat. Um, I don't have the audio hooked up to go back and forth or whatever, so the chat's the easiest way, whether you join the meeting or just literally just send me a chat. I have my phone on the side, I have a bunch of devices set up. So please just do your best to follow along because I really didn't want to have you guys try to do this on your own. Also, we don't really have enough time to postpone this lesson, especially if we want to do the lab next week. All right, so I ask you to please do me a favor and do your best with following along with me. And if you have any questions, please just send me a chat and I'm ready to answer them. All right, so in a couple of minutes, I'll start, but what you're trying to do right now is just match the wave. Make sure you color the red, the orange, the yellow, yellow, green, blue. I did light blue for indigo and then purple for violet. All right. And then you kind of have a similar thing over here. And all we're doing is coloring for right now. Right, I got a couple of you guys turned in. There's some people that haven't opened the do now yet. All right, I'm kind of looking here for the turn in to start. So it's 5:15 right now. I'd like to get started in a minute or two. So you're not doing anything other than coloring. So just color, take the picture and turn it in, and then be ready for instructions. But just want everybody to be ready so that I don't leave anybody behind. All right, so I'm going to get started. So what you guys should have had right now is a paper that looks like this. All right, and I'm not going to color in the boxes just because it'll color right over all the information, but you should have something like this. Right? The whole idea of this assignment is to kind of explain how electrons are giving off light, how we saw the other day when we were looking at the emission spectrums of the hydrogen, helium, um, the regular light, etc. Okay. So now, normally I would ask for participation, but obviously it's going to be difficult to go back and forth. So I'm going to kind of explain the stuff. Please listen. Please follow along and fill this out. Um, excuse me. If you have any questions along the way, send them through the chat because I don't have it set up the way we did with remote. And I'm not asking you guys to sign in. I just want you to look at the screen, listen to me, follow along, fill it in as we go. And if you have any questions, please send me a chat. And I got my chat right off to the right side of me so that I can answer some questions. All right. So we see here that there's a prism. All right. When white light goes through the prism, what happens is it will separate it into a rainbow or its constituent colors. All right, so that's what we're looking at here. So it will split into its colors, right? And we call that the rainbow, right? And we've seen this before, right? Now it says, why are the colors labeled in the table of Model 1 plural, like reds instead of red? Well, the reason is that there's going to be different shades of red, of colors. All right. So there are times when we can get a red bar on the spectroscope, but there can be a lighter red or a darker red. So it depends. Now, there are specific colors for specific electron movements of up and down the ladder, as we per se, the energy levels. However, we're just going to categorize them as a grouping of reds, a grouping of oranges, etc. Okay, but that's just simply the reason there. All right. Do all the colors of light travel at the same speed? Yes, yes, yes. All right. And I'm going to write that in capital letters because they all move at the same speed. All right. However, here is where we start to change. Do all colors of light have the same energy? That's a big no. All right. If no, which colors have the highest energy? And this is where I'm going to bring it to your attention. All right. When we go to the beach, what is the color light or anything that we protect ourselves from? Right. We protect ourselves from UV, ultraviolet rays. So the violets and the ones at the other end of the spectrum towards the right, if all of you guys take a look right now above the periodic table, there's a poster of the electromagnetic spectrum. There's a small little piece that's a rainbow. That's all we can see visibly. All right, the humans. Some animals and organisms can see different colors, but that's the only stuff we can see and detect. But if we look towards the right side where there's purple, right, that's what hurts our skin. But if we go further, there's X-rays. And X-rays are damaging to our skin in our body. And we know that because when we go for an X-ray, we put a lead blanket over ourselves and it protects us from the extra exposure of the X-rays. If we go even further, there's gamma rays that we can use to cure cancer, but it also can give us cancer if it's not focused from there. So as we go towards that right end of the spectrum where the light is still moving at the same speed, but it has a much higher what we call frequency. Short wavelength, but high frequency. And when we have a high frequency, it's very bad for biological material. All right, like our cells, our DNA, etc. Okay, so which colors have the highest energy? The violets / the purples. All right. All right. So if we look at that chart that's at the top, which color corresponds to the longest wavelength? Well, obviously, we're looking for the longest number. So we look at the top, we have 625 to 740. That's the longest. So the red are the longest, and the shortest are the violets. Just lost something. There we go. All right. Write a sentence that describes the relationship between wavelength and energy of light. All right. So the relationship is the shorter the wavelength, the greater the energy. I apologize. My stylus was having some trouble there. But it says shorter the wavelength, the greater the energy. The shorter the wavelength, the greater the energy. Red light, it'll warm us up. We can get infrared rays from it. All right, but it's not going to hurt you in the same way that ultraviolet rays and further rays would do it. So the shorter the wavelength, the greater the energy, and the opposite is also true. Right? So if you have all those answers down, you're going to see a picture below this. And I will scroll it back up. I just want to make sure everybody can write that down. But there are colors that coordinate with the bars. It looks very much like what we did the other day, the emission spectrum for hydrogen. Just color in the bars where it says red, red, greens, greens, etc. Just please color them in. All right, so it should look something like that. Right, number 8 and 9, you guys can do on your own. And we're not going to finish this entire thing today. It's mostly the setup, but when we do the lab on Monday, there's the lab's going to take maybe 40 minutes, maybe half the period, and then the rest of the time you're going to be finishing up this lab. So I'm going to circle some questions for you to come back to. And we did the same thing in the other classes. For all intents and purposes, we might get through it a little bit quicker than the other classes because I'm not doing a Q&A. But once again, please make sure that you're following along with what I'm putting on the screen. And if you have any questions, just send me a chat. So this way I can either slow down, go back to something, or make sure that you guys have it. So just for example, list the spectral lines for hydrogen gas. Well, the hydrogen one is the one that's up here. And so the first one, if we're reading from left to right, we're going to write something like violet, and that's going to be 410 nanometers, right? Referring to this number right here. And then just do that for all of them. And then number 9 says the spectral lines for boron were produced using the same method as hydrogen. List 3 of the colors and corresponding wavelengths for boron spectral lines as the light passes through the prism. So you only need to do the 3. Okay. Moving down. Consider the hydrogen spectrum in Model 2. Which color of light corresponds to the shortest wavelength? The shortest is the violet, and the longest is the red. And if you are seeing the redundancy in saying that red is the longest, violet's the shortest, violet's the most energy, red's the least energy, that is one of the key points that we're supposed to be getting from this lesson. And here we go. So what color of light has the most energy? Violet. And the least energy is the red. All right, question 12. Does a gas discharge tube filled with boron emit the same wavelengths of light as a tube filled with hydrogen? Use the evidence in model 2. Right? Well, you can see it's different spectral lines. All right. So one of the examples is that boron emits orange. Hydrogen did not. Right? So that's one thing that once we understand that that's what boron looks like, if we see something come up that looks like boron, we know it's boron. If something comes up that doesn't look like that, then we know it's not boron. But this is like a chemical signature for that element itself, which leads us into what question 13 is saying. The spectral lines of atoms are like fingerprints for humans. How do the spectral lines for hydrogen and boron support this statement? Right? They are specific to the element. So now we're going to get into kind of some review of what we talked about with the subatomic particles. Electrons, excuse me. Excuse me. Electrons and protons attract or repel each other. Well, electrons are a negative charge. Where'd my tool go? There we go. Electrons are negative, protons are positive. They are opposite, so they attract. Opposites attract. Right? As an electron gets closer to the nucleus, the attraction to the nucleus gets stronger. Because remember, the nucleus is positive, the electrons are negative. The closer you put them together, the more they want to go together. If you've ever messed with magnets, you can hold them out really wide and they don't have any effect. But as you bring them close together, they almost jump out of your hands. There's been a game that's gotten a little bit viral on social media. I don't know if you've seen it on Reels or TikToks or whatever. They put a string around on the table and they have a bunch of magnets, and you put one magnet here, one magnet there, and you try to keep them far away. But then if you put one magnet down and it gets too close to it, it pulls in all the other magnets that's close, and then you take them out, and then those are your pieces. It's kind of like domino style game. It's an interesting thing, but if you've seen it, that's kind of, what's going on with an atom. For an electron, number 16, for an electron to move from an energy level close to the nucleus to an energy level far from the nucleus, you would need to gain energy. Gain energy. Remember, going up a ladder, we need energy. To come back down, we can fall back down with no energy. All right, it can just go because we've already stored that. So for an electron to move from an energy level far from the nucleus to an energy level close to it, it will lose energy, right? And FYI, I know it asks it, but I want to make sure you get this point. When it loses the energy is given off in the form of light. All right, so we are going to be using the Bohr models today. Even though I've told you guys that it really doesn't act like that beyond the second energy level, for our example in understanding this concept of electrons moving up and down levels, the Bohr model is perfect for this. All right, so that's what we're going to be introducing to you today. So I'll read this, all right, read this right here. You can read along with me as I read aloud. Niels Bohr modified Rutherford's nuclear atom model to explain how light interacted with the electrons in an atom to produce spectral lines. His model included electrons orbiting the nucleus at a specific energy levels. Electrons absorb energy from various sources, electricity, when they move from lower energy levels to the ground state to higher levels, excited state. Energy is released as electrons return to their lower energy levels. So 18, is energy absorbed or released from the electron transition shown in the diagram to the right? Well, since we have an arrow moving away, we are talking about it gaining energy. It's absorbing the energy. All right. So it is moving away from nucleus. Okay. So away from the nucleus, it gains energy. When it moves towards the nucleus, it's losing energy and it gives off that energy in the form of light. Okay. So I'm going to give you guys a couple of seconds, maybe a minute or so, to kind of do this one part on your own. All right. So you have 4 pictures of the Bohr models. All right. Number 19 is what you're going to do right now. And I want you to circle the letter. So A, B, C, or D. All right. And identify the model in model 3 that depicts a hydrogen atom with an electron moving from an energy level 5 to an energy level 2. All right. So take a couple of seconds. So where do we see an electron going from level 5 to level 2? All right. So hopefully by now you figured out that it was B. All right. If you look, there's 1, 2, 3, 4, 5. So if we follow that back around, we go from here, all right, down to level 2, which is right here. Now, when we talk about energy levels, remember we talked about the Schrodinger equation, quantum numbers, blah, blah, blah. In this chemistry book and this activity, you're going to see that they depict the energy level as N, right? The letter N. So we're going to go from N equals 6, sorry, N equals 5 to N equal 2. All right. Keep B circled, only B circled. Take a minute or two and see if you can do the N equals to N equals for A, C, and D. All right. So A, if you're looking at it, it should have been N equals 6 to N equal 2. We did B. C is N equal 4 to N equal 2. And this one is N equal 3 to N equal 1. All right. One more step I want to talk to you guys about, because we're going to do this again in the second part of the activity, is I want you to write how many levels did the electron move according to the arrow. It's a simple subtraction. So if we started at 6 and we went down to 2, that's 4. So I want you to put a 4 in a square, right? Put the 4 in a square. That is going to indicate the number of levels. So B went from 5 to 2, so that was 3 levels. C, 4 to 2, so that's 2 levels. And 3 to 1, actually, sorry, that was 3 to 2. 3 to 2, and that's 1 level of falling. All right, so if we go down here to answer the questions, the electron transition releases energy because we are going back towards the nucleus. The electron moves from a higher energy state to a lower energy state. And is light absorbed or released? It is released. All right. So now 20 is what we just did. Let's look at 21. Which of the electrons transition involves the most energy? So the concept that we're looking for is, where did the electron drop the most amount of levels, the greatest distance, excuse me, the greatest distance. And in that case, it was in A, and it went from n equals 6 to n equal 2, right? Which was 4 energy levels. Explain why this transition involves the most energy based on your understanding. All right. Just say it moved the most. I know I'm oversimplifying that, but that's fine for this case. All right. I'm making sure you guys understand the major components, which is what we need for the lab. Explain why a single atom of hydrogen cannot produce all 4 hydrogen spectral lines. Because it only has 1 electron. Right? It only has 1 electron, and each electron can only move itself. All right? But here's the problem. When we were looking at hydrogen the other day, we didn't only see 1 spectral line. All right? But here's the thing. Is there only 1 hydrogen in the spectral tube? No. Okay? So there are multiple atoms in a sample. Okay? So one atom maybe go up 1 level, but another atom's electron can go up 2 or 3. All right? So just understand that 1 atom can't do it all, but very rarely are we just dealing with 1 singular atom anyway. Okay. So that got us up to the extension. That's where we needed to get for that packet. So if you can, please take out the other worksheet with the waves that you guys put in there. All right. So have this out and take out a ruler. Can also one of the interns just message me to give me a thumbs up if everybody's in the right pace, because I don't want to move on to this until everybody's there. Awesome. Thank you, Mohammed. All right. So what we need to do next is, please take out your ruler. What you're going to do is you're going to line your ruler up with this edge right here. Okay? Because what we need to do is we need to make a 2.5 inches. All right? Make sure it is inches, because if you look on the table that I gave you guys, this space right here is 2.5 inches. That's where it's going to go. So what I need you to do is I need you to measure the violet one, measure over 2.5 inches, wherever that is, make a point. Go down to maybe yellow, measure off 2.5 inches, make a point. Then using your straight edge, make a line that goes straight down. All right? Because eventually when you guys are going to cut this out, it needs to be this whole piece, not, all right, I repeat, not from here 2 inches over. You need to include these in your 2.5 inches. Okay? So all you're doing right now, I'll re-erase this so that we can do this and it doesn't look sloppy. You're going to line your ruler up. Yeah, let me use the highlighter. You're going to line your ruler up with this edge. All right? Measure out 2.5 inches. Draw a point. Then go further down the sheet, measure 2.5 inches, make a point. And then you'll draw a line down so that eventually when we get to cutting this out, every strip will be 2.5 inches, and it's very important because we're going to be doing something that if it's less than 2.5 inches, your number is going to be off. If it's more than 2.5 inches, your numbers are going to be off. So just take your time measuring this and just draw a line straight down. Okay. So eventually what you guys are going to be doing is you're going to be calculating the number of waves that are in this 2.5 inches. Well, I haven't taught you how to calculate a wave yet, so I'm going to do this right now. To calculate one wave, there are parts to a wave. Let me make this a little bit bigger. All right, there's parts to a wave. There's called crests. All right, good. Here's a crest. You don't have to write this down on yours. If you want to write this stuff down, write it beyond your line that you're cutting off. So, all right, so like this side right here, right? So I'll actually do that. It's just the way it blew up on my end. All right, let's get my computer to catch up. All right, so the peak of a wave, that's a crest. The bottom is called a trough. But a wave, one wave, is from crest to crest or trough to trough. Now, all of your waves, if you look, it's going to start at a crest. So let's just start from crest to crest. So if I wanted to calculate from here to here, look what I'm doing. All right, here's one wave. From here to here, that's two waves. If I got to here, which I didn't, that would end up being 2.5. But I'm about right here. So it's kind of halfway in between. So I would say this is 2.25 waves. All right, you're going to do your own estimate. It doesn't need to be perfect. I do have a buffer of what I grade on, but be careful. If it doesn't get from one peak to the next, it's not a full half. But that's how you count the waves. Okay? All right. So now let's go to the more difficult part down here. All right. If you wear glasses, please put them on. These graphics are good. They're the same as what we've been working with. However, what's it called? Some of it is a little bit difficult to see. I did try to make the lines a little bit darker in my past worksheets, but just go along with me. What I want you to do with each one of these board diagrams, there's 7. I want you, just like we did in the previous activity, I want you to write from N, whatever level it's starting at, to whatever level it's going to. And then I want you to put in a square the amount of levels it fell. So if we're looking at this one right here, we are starting at this level right here, and it's going to level 3. All right, so this is 3, 3, 4, 5, 6. This is going from n equals 6 to n equals 3. So that means it fell 3 levels. All right, so take a minute, or 2 minutes actually, and try to do the rest of them. And the outermost ring is 7. So it goes from 1 to 7. The next one was n equals 7 to n equal 1. So that is 6 levels of drop. Right, so the next one, n equals 7 to n equals 6, which is 1 level of drop. The last one on the end is n equals 7 to n equals 5. The bottom left, n equals 5 to n equal 1, which is 4 levels of drop. All right. N equals 6 to n equal 4. That's 2 levels of drop. And then the last one is n equals 6 to n equal 1, which is 5 levels of drop. Okay, so one thing that I want to say that this activity does oversimplify what is actually going on, but it's fine. It's still the concept is going to be there. All right, but we are given, excuse me, the 7 different colors, and the highest energy is going to be one color, the lowest energy is going to be the other color. All right, and everything in between. And how do we know the colors? Right, well, right from up here. All right, so the violet is going to be the most energy. So which is the most energy? The one that dropped down the most. All right, the red will be the least energy. So if we go back to here, sorry. All right, so we can kind of start to label them where there was only one level drop. All right, that'll be the red. Where the most, where we had 6, all right, that'll be the violet. All right, so let's just start there. I could choose black. All right, well, that was supposed to be purple, but it doesn't matter. You can still see it. Okay, but then we need to find the ones in between. But I don't know if you guys recognized, but there are 2 twos. Well, one thing that I want to bring back to your attention is if you remember correctly, when I showed you guys the ladders of the way that the electrons go up and down, in real life, a ladder, they're even rungs. But in an atom, it's not even. There's much more space in the first rung than there is in the second, the third, the fourth, and so on. So if we look at this one drops from 7 to 5. This one drops from 6 to 4. So because it is dropping larger distances, all right, the 6 to 4 is a larger distance than the one going from 7 to 5, right? That's going to be the one that is the next least energy. So this one is going to be orange, followed by this two being yellow. Okay, so then it does get simpler from there because all of the numbers do rank the way they're supposed to. All right, so we go red, orange, yellow. 3 is going to be green. All right, then we get up to 4, right, which will be blue. Right, which will be 4 right here in blue. And then we will choose our indigo, which will be this last one, 5. All right, and as we said, violet's up at the top. Okay, so what you're going to be doing with this page is if you pull out the one that is the table, all right, the table piece, there are directions that are on the back. You guys are going to be coloring, all right, and cutting. You guys have about a good 40 minutes, all right? What you need to do is you need to make this chart properly. One of the things that I want to make a suggestion to, all right, let me pull up, all right, when you guys are putting in your Bohr models, right, what I want you guys to do, all right, you have your Bohr model, you need to make sure that when you make the cutout, you keep the arrow, all right, and we're going to put the n to whatever to n equals whatever. We're going to put that in there, but I want you to stagger them. So the next one, I want you to put on the right, and then you'll write over here n equals blah, blah, blah to n equals blah, blah, blah. All right? Then you put the other one over here, then the other one over here. Go back and forth because otherwise they are not going to be following along. Please make sure, all right, this is the part where is on your own. These directions, follow them. All right, it's going to tell you to look up some stuff. Look up on Google, where's that instruction? All right, so let me read these so this way, you know, there's none of you can say like, oh, I didn't understand. All right, so using markers and crayons or colored pencils, color each wave. We did that in the do now. Cut out each wave, including, all right, I'm going to highlight that, including the wavelength measurement, right? It's the most common mistake every year that students make, that they don't cut out that wavelength measurement. You need that. Make sure that it is a 2.5-inch section. You're going to glue each wave to the corresponding box. I put out glue sticks. There are scissors. Excuse me. Please make sure that you don't leave scraps on the floor. To calculate, excuse me. To calculate the frequency, count the number of waves over the 2.5 inches. That's what I showed you from peak to peak. All right, answer the question. Now use number 4. Now use the 7 Bohr models to match each wavelength. We kind of did that together. All right, I showed you what color goes with it to kind of just bridge the gap and make sure you understood what you were doing. Glue the Bohr models to the corresponding box. Please, like I said, stagger them because otherwise it's not going to fit. And please make sure that you cut out the wave of that's on the board, not just the circle. All right. And then the last part of this, question 5. The farther the electrons travel between the ground state and the excited state and back, the greater the amount of energy released. Now rank them. Least energy is 7. Greatest is 1. So be careful, okay? The greatest energy is 1. The least energy is 7. All right? You have more than enough time. You guys have a little bit of an advantage because, what's it called? I didn't have the back and forth questions, so the class went a little bit quicker, and I did most of the stuff for you. But use this time to try to, finish it, get it pasted. If you cut out your stuff today and you don't finish, please make sure that you don't lose your pieces. You don't have to do it for homework, but if you know what you're doing and you want to just get it out of the way, try to get it done in class and finish it up. All right. And I left the extension question in the packet. I left the extension questions off for you guys to do during the lab, but it's there. It is eventually going to be done. Okay. I'm going to stop recording this meeting. So hold on a second. And then I'll leave this open for you guys to chat me and ask questions.